Hello, and welcome back. Today we're getting into statics, which is basically what's needed for something to be perfectly stationary or still, like a building or a bridge. So this is you might take a class strictly on this in college if you go into engineering. And in order for something to be perfectly static, there's two conditions that need to be met. One is all the forces on that object must cancel, and all the torques on the external torques on that object must also cancel. Okay, so we're going to look to see whether or not forces cancel and if torques cancel, if something is going to accelerate or rotate. Okay, so this object right here, so this is just a stick of wood. This is the axis of rotation. This is in space. Is this going to accelerate? No, the forces are going to cancel. I've got 100 to the right and 100 to the left, so it's not going to accelerate. Is it going to rotate? No, because let's say that this distance right here is 1 meter. I've got 100 Newton meters of clockwise torque, and I've got 100 Newton meters of counterclockwise torque. Okay, so the torques are going to cancel. So this object would fulfill the conditions of being static. Okay, its motion is not changing. Let's look at this. Will this object accelerate? Yes, it will, because it's got 200 newtons of force to the right that's going to cause it to accelerate. Will it rotate? No, it will not. It's got 100 newton meters of clockwise and 100 newton meters of counterclockwise. These two torques are going to cancel, assuming this is our axis of rotation in the middle right here. Okay. What about now? Will it accelerate? Will it accelerate now? Yeah, there's still 100 newtons of force to the right that's going to cause it to rotate. What about this? How is this changing its rotational motion, or is it? Is this going to create torque? No. Remember, any force going through the axis of rotation causes no torque. What about this object now? Will it accelerate? No, because I've got 200 to the right and I've got 200 to the left, so my forces are going to cancel. Will it rotate? Okay, these two torques cancel. This one causes no torque, so it's got zero Newton meters of torque left on it, so it will not rotate either. So this one will be static. Okay. What about this? Will this object rotate or accelerate? Will it accelerate? No, it's got 100 newtons to the right and 100 newtons to the left. 100 newtons to the left, 100 newtons to the right, so it will not accelerate. Will it rotate? Will these torques cancel? No, it will not. They will not cancel because they're going to add. They are both in the clockwise direction. So this has 200 Newton meters of clockwise torque. So this will just spin up like so. All right. What about this? Will this accelerate? Yeah, 150 to the right. Will it rotate? Sure it will. Okay. What about now? Will this accelerate? Yeah. Will it rotate? Yeah. Okay. What about now? Will this accelerate? Okay. Will it accelerate? Yes, because there's 50 newtons of net force to the right. Will it rotate? It will, because these two torques are in the same direction, so they're going to add. They're not going to subtract. Okay. If this force were on the other side, these would cancel, assuming this one is halfway in between, which I'm not trying to be tricky here. But it looks like it's about half. It should be about half. As that happens over here now, will this object accelerate? 150 to the right, 150 to the left. It will not accelerate. Will it rotate? Well, this one has 50 Newton meters of torque. This one has 50 times a half a meter, 50 Newton meters of torque. These two torques are going to cancel, okay, clockwise and counterclockwise. This one's not going to create any torque, and so it's not going to rotate. So this one would fulfill the criteria of being static. Okay, so statics, getting things not to move. It's an important field of study for civil engineers especially. So, but like I said, you might take a semester-long class just on statics. Okay, so when you do this, there's a lot that goes into making sure a building or a bridge can support itself and its load. You know, notwithstanding, you know, all the moving loads like tractor trailers driving down a bridge, withstanding winds and earthquakes, withstanding the load of the material itself. But the first thing we're going to get, we're going to look into, and this is as far as we're going to get, is really just, can the thing support its own weight? And so that's what we're going to look at. And so there's the two criteria that we're going to look at is A, all the forces have got to cancel, okay, meaning lefts have to equal rights, ups equals downs, okay, but that isn't enough. If I had the other criteria that needs to be met is that the torques have got to cancel, and there's internal torques and external torques. We're just looking at the kind of a little bit of both, really. And we can say that as the torques clockwise equal the torques counterclockwise. Or we can say that the sum of the torques equals 0 if you play the positive negative game, which I normally don't mess with. So let's skip that. So let's say we've got a massless meter stick. Okay, we do that to make the problem easier. Obviously, where do these physics teachers get their massless meter sticks? At the massless store. So we hang a 1 kilogram mass at the 25 centimeter mark. So this is 0 centimeters. This is 25 centimeters. What is the force exerted by each spring scale? Basically, what does each spring scale read if everything is static? So first thing we do is we say ups equals downs. Well, the first thing we do is we assume a direction of a force. And we say that one spring scale on the left is pulling up and the spring scale on the right is pulling it up. Okay, we call that one A arbitrarily and that one B. And so then there's 9.8 newtons from that 1 kilogram force that's down. So we say ups equals down. So write an equation. The ups, FA plus FB equals my down, which is 9.8. And so that's step 1. Step 2 is all the torques should cancel out. Okay. Now this meter stick isn't pivoting around any point. It's not pivoting. It's stationary. So what do I use as my pivot point? The answer is you get to pick. Here's how you choose wisely. You choose a location that has an unknown at it. Okay. And preferably does not have knowns at it. So by a known, I mean this 9.8. We would not want to choose this. This would be our least favorite choice. Okay. We could choose D. I would not want to choose D. We want to choose a location like A or B where it has an unknown quantity at it. The reason we do that is that if I put my pivot point there at location A, force A creates no torque, which means it is out of my equation, which means I get to solve an equation with one variable as to one with two variables, which in my book is a win. Okay, so you can choose any point, okay, but it's smart to pick one that's got an unknown at it. Okay, and you know, if it ends up being a wonky choice, you can always go back and re-choose. But we're going to choose location A, and what we're going to say is, so this is my pivot point. Okay, the torques clockwise and torques have to equal my torques counterclockwise. So first off, we'll look at force A. Which direction is the torque going to be from location A, from force A? Well, if my pivot point is right here, okay, this creates no torque, which means that it is not on either side of my equation, which is good because it's an unknown. This 9.8 newtons, if this is my pivot point right here, this is going to be on my clockwise side. Okay, so that's going to be 9.8 times 0.25. Okay, that has to equal my counterclockwise torque. Okay, and so that's going to be FB times 1. Okay, so now look at, I've got an equation that's got one unknown in it, which is good. I can immediately solve for FB. FB equals 2.45. going back to our original equation where we said that the two up ones had to add up to equal 9.8, had to add that, then I substitute in FB, and I get FA, and I'm done. Okay, so that's that example. Okay, another example here. A 65 kilogram person stands on a 6 meter long plank, ignoring its weight. Where should they stand so that the tension in the left cable is equal to 180 newtons? Okay, so we're going to solve this as one step. I'm not really sure why this example is right here. I'll probably move this example to another location, but this just shows you a good way of choosing your axis of rotation. So we don't actually have to say ups equals downs here, although it certainly wouldn't be a bad thing. It wouldn't hurt anything. We've got these two forces. This one on the left is 180 newtons. Okay. Now this person's going to have a weight of about 650 newtons, and the left scale reads 180, which means they're going to be closer to the right side. Not that that really matters where I draw the person, but we're going to go ahead and say where am I going with this? But we are going to say that our clockwise torques equal our counterclockwise torques. And before we start calculating torques, we need to figure out our axis of rotation, our pivot point. Okay, remember what I said, you want to choose a location with an unknown on it, which means I don't know how much this scale is pulling up. I could figure it out, but I don't know what it is right now. So I'm going to choose this to be a location on the very right length of the plank to be my axis of rotation. And then I'm going to say my clockwises equal my counterclockwise. Okay, so my clockwise would be this 180 Newton force because it would swing us around like so. So that's 180 times 6 because this is a 6 meter long plank. Okay, equals 637. I calculated the weight of the person, 637 newtons, times x, where x is the lever arm distance. It's the distance from that one end. And I've solved this in one step, so 1.7 meters. So this one was no big deal. I could have chosen anywhere along on this plank to figure out to solve this problem, but making a smart choice of putting it here made it so I could solve it in one equation. So always choose where an unknown is, preferably not the unknown you're looking for. Okay. Next, we've cantilevered some signs. So if you've ever seen those park signs, they will say welcome to blah 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 state park or national park. A lot of times they're cantilevered, which means that you've got two supports on one side, and then there's a beam that extends over, and you hang your sign from that. It sticks out over the near the road. What we want to do is find the force exerted by each one of these posts. And we're not having a sign for simplicity. We could easily add a sign to this, but we're just going to look at the weight of the beam itself. So this is a 25 kilogram beam, and so we're going to figure out what the force is exerted by each one of these. So there's another trick. So you may not necessarily know what direction each force would be in. You can always guess. And if you guess wrong, your answer is going to end up being negative, and that's no big deal. You just know it's actually the opposite. So I'm going to say that both of these posts are pushing up on this beam. Okay, so force A is going to be up on the beam, and force B is going to be up on the beam. Okay, so I'm drawing this out. Okay. And you can see I've already chosen my my axis of rotation, my pivot point to be the left side here. And again, it always helps to draw a picture. We've got dimensions labeled, so 5 meters away is FB, and the beam is 16 meters long. It's a very long beam. And so our weight, the weight of the beam, which is 245 newtons, we're going to put it 8 meters from the left side. Okay. And then we'll go ahead and solve. Okay, so first off we'll say ups equals downs. Okay, so FA plus FB, my two ups, have to equal my down, which is 245. Okay. Then we're going to say our clockwise torques equal our counterclockwise torques. So we're going to choose location A as my pivot point. Okay. Force B is going to be my be counterclockwise. I've got that labeled wrong. This should be a counterclockwise torque, and that should be clockwise torque. But I think you'll be able to figure it out from there. So my counterclockwise torque is FB times 5. So the equations are still going to work out the same. FB times 5 equals my clockwise torque, which is 245 times 8. 245 times 8. And we get that the FB is equal to 392 newtons. Okay. Now I know FB. I'm going to plug that into my first equation. FA plus FB equals 245. And I get that FA is equal to 147 newtons. Negative 147 newtons. Sorry. Okay. And what that means is that FA, instead of pointing up, is actually pulling the beam down. And this probably makes sense. This end would have to be nailed in order to keep it from pivoting up. It would tend to want to pivot over B. But again, I didn't have to choose B as my pivot point because I didn't want it to pivot around any point. Okay. Last example, or sorry, 2 more examples. So here we've got a beam, and it's supporting a 11 kilogram sign or something like that. 2.5 meters from the pin connection. So this is a pin connection, like from PoE. So kind of a lot of connections with PoE, this unit. Now, this can rotate. Okay, this thing can rotate around, but it can't move left to right, and it can't move up and down. So there's an A in the X direction, there's a force A in the X direction, and there's a force A in the Y direction, or at least there could be. So we've got this beam. The beam itself is 7 kilograms. Okay, it's 3 meters long. Okay, so that 7 kilograms, 7 times 9.8, we're going to put it 1.5 meters from the left side. This 11 times 9.8, we're going to put it 2.5 meters from the left side. Okay, and then here we've got this. This is a tension component. Now this is going to have an X and a Y direction. Okay, we're going to go ahead and break it apart into its X and Y components and deal with those. But ultimately, what we want to find is what is the tension in the cable. Okay, so the first thing we do is we draw things out. We get everything labeled. So I've got my AY and AX from that pin connection. I've got the 7 kilograms from the mass of the beam. I've got the 11 kilograms from the sign or whatever. Okay, and then we've got the X and the Y components of the tension. Okay, the first thing we're going to say is lefts equal rights and ups equals downs. So left equals right. That means BX has to equal AX. Okay, those are my only X forces. Okay, ups equals downs. AY plus BY equals my 2 down forces, 68.6 plus 107.8. So equals 176.4. And the next thing I'm going to do is say my torques clockwise equal my torques counterclockwise. So left equals right, up equals down, clockwise equals counterclockwise. Okay, so let's start on our clockwise side. So we're going to choose location A. We're going to choose that because it's got unknowns in it, and it's not asking for these unknowns, so I don't care about these unknowns, so I don't want to find those. I don't want to choose a location of a known, and I don't want to choose this location because I'm trying to find out about this location. So that would be a little silly. I mean, we could certainly do it. It would be no big deal to choose this as our pivot point, but I wouldn't do that. It just causes you another step. So 68.6 times 1.5, okay, times 107.8 times 2.5, okay, equals 3, because we're 3 meters, times BY. Now, I'm not putting BX in my torque equation. Okay, do you know why? Which way is BX going to cause rotation, clockwise or counterclockwise? It's not. BX points directly at the axis of rotation. So therefore it's going to create no torque, so I can leave it off my torque equation. Okay, BY is going to cause counterclockwise rotation. Okay, so solving, we get BY equals 124 newtons. Okay, so I found BY in one step. The last step, Once you know the vertical component of Vy, the last step is to just figure out what the actual tension is. So you've got an angle of 36 degrees from before, 36 degrees, and I've got the vertical component. So it says what's the actual F sub t. So that's your hypotenuse in this equation. So we say the sine of 36 equals 124 over b. Yeah, I probably should have written that as b instead of F sub t, but it's really b. And you get that b, or F sub t, equals 211 newtons. Okay? All right, bear with me. We got one more example, then we're calling it quits for the day. All right. This is the old ladder up against the wall problem. And I say that because I saw this problem in my physics class in college. And it's in the textbook, and it's just one of those problems that you do when you're talking about statics. The old ladder or something hanging up against the wall. Okay, so we've got a ladder. This is my yellow thing. It's got a roller here. It's also a frictionless wall. Okay, so I'm just telling you there's no force of friction or anything like that. So the ladder's got a mass of 12 kilograms. It's supported at the floor and at a frictionless wall, and we want to find what are the forces acting on the ladder. Okay, and I give you it's a 3, 4, 5 triangle. Okay, so at the floor, okay, I called it A, B, and C. So I don't know why I called it that, but there's a normal force off the floor. Okay, I called force A. There's a force of friction at the floor. Okay, I called force B. I don't know why I didn't just call it force of friction. Okay, and then there's another normal force acting at the wall. Okay, away from the wall. Okay, I called that FC. There's no force preventing this from sliding down. There's no force of friction here because that would just murky up the waters. So that's why it's a frictionless wall. There's no force of friction here. It's just the normal force. And then there's the weight of the ladder, which we put right in the middle of the ladder, and it points straight down. Okay? So so the first thing we're going to say is ups equals downs and lefts equals right. Okay? So ups, I've got force A, okay, and I've got one down, which is my weight, which is 117.6. So I know one force right off the bat. Okay, that was easy. Okay, the next step is left equals right. So F sub C equals F sub B. I've only got one left and I've only got one right, so they have to equal. Okay. The next thing we have to do is figure out either F sub C or F sub B. Okay. I'm going to choose this to be my axis of rotation because I have two unknowns here. Okay. Well, technically I do know this one, but as when I chose this, it was an unknown. Okay, and I've got one unknown here, so that works out good because this will still be in my torque equation. These two will not be in my torque equation. I don't want to have them complicate things anymore. So that way I'm just going to have one torque here and one torque here. Okay, so torques clockwise equals torques counterclockwise. So let's see, 117.6. Now this is where we apply a trick. Okay, remember how I said you could look at the force of and torque two different ways if the force and the lever arm were not perpendicular. And so if I consider the ladder to be my lever arm, okay, this force here is not perpendicular to it. I could use trig and I could figure out the component perpendicular and the component parallel. And I could do that same game here, but I'm going to use the second way, where we use the entire force, but we shorten up the lever arm. Okay, so try to follow along here with me. So, so this is my pivot point here. You got to keep that in mind. Okay, remember the method for the second method. Draw a line through the force. So draw a line through the force, and then your lever arm is the distance, perpendicular distance from that to the pivot point. Okay, So think about this triangle right here, similar triangles. We're halfway up because we're halfway up the ladder, which means we're halfway over. Okay, so instead of 3 meters, it's 1.5 meters. So it's just half this distance here is 1.5 meters. So 117.6 equals times 1.5. Okay, now then we're going to do the same thing with F sub c. We're going to draw a line through the force, and our perpendicular distance is the lever arm. Well, that's this side of the triangle here, this big triangle, okay, which is 4 meters. So this is one of those situations where it's just a heck of a lot easier to use the second method. So if I solve for F sub c, I get 44.1, and that equals F sub b. Okay. All right. Thanks for sticking through with me. Hopefully that made some sense. Good luck on the problems.